What's up, y'all? For section 7.4, it basically just proves that Lagrange equations, um, when you use them, you don't need to know the constraining forces because it can take care of them for you. And so we're just gonna outline that in this section. Okay, so the things you need to know for this chapter, that constraining forces are not necessarily conservative. So they might not, so like they don't depend on, or yeah, they do not depend on position and position only. They can depend on a lot of things. And then the Lagrange approach eliminates the need to know these constraining forces. And so that's what this chapter is going through and kind of proving, is that you don't need to know them, because in some cases you do need to know them because you're like, how will they affect my system? And Lagrange is like, I need them not. And so we're just sort of going to go into that. Um, so the first thing we're going to do is the action integral is, so in order for this to like, in order for this to be true, the action integral at um, at the right path has to be stationary. So that's just sort of what we're going to prove. And again, if you watch the 6.2 video, it does the exact same thing that does. So what we're going to do is we're going to start with sort of an arbitrary function of an arbitrary function, but this is the arbitrary function, this little r, that we know to be perfect and correct. And then we're going to add an arbitrary function to it, but it's all going to vary with the time. So since we have that, we can then say that this stationary action integral that we're looking for, it's going to look like this. It's going to be the integral from time 1 to time 2 of the Lagrange of this r vector, or so the big R vector, plus that big R vector's derivative. And it's also going to have to do with t. And then all of it's going to be integrated by t. So that's what we can say from here. But what we do want to note is that the change in s is going to be equal to this s function plus whatever s was initially. It's that initial position of s. Yeah, so we're going to start with that. And we can say that that's the same for this, the Lagrange here, that its change is going to be equal to the Lagrange plus whatever the original one is. And that's just like your basic definition of change. So I'm going to write that down too. Let's change. This is sort of how the book denotes change, just so you know it's not the triangle. And then what we note here is that that initial Lagrange is just going to be whatever function is the true stationary function. So that's where that starts to get really nice for us. So the next thing we're going to do is we're going to kind of write out what that means further. So we're going to take, I'm do it in blue now, the change in the Lagrange. It's going to be equal to, so this is where we use the Lagrange equaling kinetic energy minus potential energy, and we're just going to sort of apply that to this change that we see. So it's going to be m times, now we're going to plug in for the big R, we're going to plug in values that we have for it. If it'll let me. I'll give it a second. Okay. That's RV right there. So that's just the change in kinetic energy. And then we're going to subtract, here I'm going to go into the full screen. We're going to subtract, let's make sure, the change in the potential energy. And again, we're going to plug in our smaller values for the big R. All right. So from there, we're just sort of going to simplify it, and we get that M is going to M times R dot plus the dot product of, whoa. So then the dot product of this arbitrary function and its derivative in time. And then minus said arbitrary function times the gradient of this u, and then it's going to be plus 0 e squared, but we don't need that, so we're going to drop that. And we're just going to sort of continue on what we can now say. I'm going to scroll down, leave that there. So we're going to put this back into terms of s, of the difference of s. So I'm going to use red again. So the difference in s is going to be equal to that integral of over time of that difference of the Lagrange. So I'm going to write that out below because it's just going to take up so much room. Do you like that I decided not to erase? Okay. So it's just going to be that second function right there. There we go. And then all that dt. All right. So now that we have that, we're just going to look at the endpoints. Get new color. At the endpoints, this is going to be 0 and this is going to be 0, because just like in 6.2, that's really our only condition for that function, is that it meets the function that we want, so r, little r, at the endpoints. So we can then simplify that. And we end up getting that the negative integral of t1, t2 is going to be epsilon, that's epsilon, dotted with the force constraint. So that's going to be, that's why this is here, right here. That's where we're getting that from. And dt, which ends up, so what we know about the constrained force, just by definition of what it was, it goes a bit more background information into this in the book, but I'm just going to tell you it. This is perpendicular to the surface, and this is parallel to the surface. So they're perpendicular to each other, and their dot product will equal 0. So the entire integral is just going to be 0. It can be a constant, but the textbook just kind of leaves it at 0, just like 0, 0. So that's what we're doing. And basically what that says is that the constraining forces can be nullified. And that is why Lagrange is so great to use. Another prime example of like this problem and why that all works out to be 0, this was the author's argument for why it's 0, is because of Hamilton's principle. So that's what he applied to in that, to make sure that it was 0 and not a constant. So then our final proof for it, I'm just going to sort of like draw a good old line here. This is our final proof. What we're going to do is we're going to prove Hamilton's principle works for those variations of the path that are constrained with the constraints, which means we can't use Cartesian, but we can have like general forms of coordinates, which is kind of like we already did this. Literally, what this does is it brings up that derivation from 6.4 that we saw in like 7.1, 7. I think 2 and 3, it was in there too. It brings it up again. So I'm just going to sort of write it back out for you because going through it, there was like no difference between how he got the one I'm about to write down and how he got the one from the others. Like it's not even denoted different. It is the exact same thing. It's just that this proof is like the summary of how this all can work. And so he repeats himself so much. I like blue. Okay. S equals integral from time 1 to time 2, Lagrange, Q1, Q2, Q1, Q2. Since I'm only going to Q2, this sort of signifies that I'm only in like 2 dimensions. Don't care which 2, just in 2 dimensions in general, which means that I'm going to have those 2 different Lagrange or Lagrange forms of this right here. And then this is going to be the derivative of time. Q dot 2. Okay, so those are the 2 general equations that you get from just doing 2D motion. And since you can see a pattern in those, you sort of states the pattern this time without really deriving it. And that's just that general of the Lagrange that we've been seeing for the past couple sections. It just shows up yet again, and just expect this guy to show up everywhere, honestly. So yeah, that's that. And then, come on, you can make a dot. All right, maybe you can't. And then we're going to specify, whoa, okay, that's fine. We're going to specify right about here that I'm going to make sure we know that I is any number between 1 and whatever we want. And that's all this chapter goes over. And that's really just how it works. Is it works because it's really built into just how it works. This is key right here. Using Hamilton's method there is how he got there, which we know it to be true from other chapters. So yeah, it's kind of it. The next chapter is just a bunch of examples, so it really dives into like how to use it and why to use it. So